Hello, everybody. Today with us is a pleasure to have Federico Pichi. Federico is a joint postdoc between CISA and APFL, and today he will talk about artificial neural network for bifurcating phenomena modeled by nonlinear parametrized PDEs. Thank you, Federico.
So thank you, Maria, for the introduction. I'm Federico Pichi, and the topics of today will be, as Maria said, the artificial neural network for bifurcating phenomena modeled by nonlinear parametrized PDEs. This is a joint work with Francesco Ballarin, Gianluigi Rozza, and Ian Staven. So let me give you a wide overview of my research project that I carried out during my PhD, since this will be the starting point for the today's discussion. So my main research interest is concerned to bifurcation theory, and in particular, since the reconstruction of bifurcation diagrams requires many query context, which is usually unaffordable by means of high fidelity standard discretization, we tried to investigate the applicability of reduced order models to these nonlinear and ill-posed problems characterized by bifurcation points and uniqueness issues. In fact, we studied many models coming from very different physical contexts, such as the von Karman equation and the pay-elastic laws in continuum mechanics, the Gauss-Podolsky equation in quantum mechanics, and the Navier-Stokes system in fluid dynamics. Moreover, we investigate also many other directions, trying to answer to some open questions with external tools, in the sense that we tried to investigate and find all the possible existing solutions to a given model through a reduced order model approach to the deflated continuation method. We designed several optimal control problems in order to steer or drive the bifurcating behavior of such complex system. And finally, we also developed an integrated TER-BNN approach in order to avoid the application of intrusive EV reduction strategies. And of course, the latter will be the topics of this talk. Let me also mention the fact that all the simulations were performed within the open source libraries Phoenix and Benix for the high fidelity and reduced order approximation of the PDEs. So this is the outline of the presentation. I will start by giving you a brief introduction to bifurcation theory with some example and its their approximation through the standard Galerkin infinite element method. Then I will move to the intrusive reduced order models with the pod-Galerkin approach, and then I will introduce you the non-intrusive artificial neural network technique through the PodNN methodologies. And finally, I will show you some results concerning multi-parameter application to the Navier-Stokes equation for two test cases that are the Coanda effect in a channel and the triangular cavity flow. So my PhD project started with the question, what have in common complex models coming from very different physical contexts? Well, a partial answer to this question is contained in the videos below. In fact, as you can see, complex models contain nonlinearities which usually involve, sudden changes in the qualitative behavior of the solution, and these sudden changes are called bifurcation. An example can be given by the a beam under compression, which deforms in a quantitative way until it reaches a certain critical threshold at which the beam buckles. From a more mathematical perspective, we can introduce the ODEs by Landau that describes the hydrodynamical instabilities. And by classical ODEs theory, we can study the stationary points of this model. And what we find is that, actually, the point mu star equals 0 is the aforementioned critical threshold for this model. In fact, for mu less or equal than 0, we have the existence of a unique solution that actually is the trivial one, while for mu greater than 0, we have 3 coexisting solutions. Of course, we can study the stability properties of this solution. And in particular, this is the classic example of what is called supercritical pitch for bifurcation that is depicted in the figure on the left in the bifurcation diagram. The bifurcation diagram is essentially a visualization technique that allows us to understand and to investigate the behavior of the solution manifold with respect to the parameter space and by means of some specific feature of the model. Let me also add that the point mu star is said to be a critical point or bifurcation point because in such point we are violating the hypothesis of the implicit function theorem in the sense that the Jacobian is no longer invertible, and also is the point in which we are losing the uniqueness of the solution. So now we can move to the approximation of parametrized bifurcating PDEs models. So in particular, we don't want to study simple ODEs, but we want a general framework for nonlinear PDEs. And so we can represent a generic nonlinear PDEs with the parametrized mapping G that goes from the solution space X times the parameter space calligraphic P into the dual space of X. And our goal will be, given a parameter mu in the parameter space, we will seek the many possible solution X of mu, such that the strong form of the PDEs in equation 1 holds. Of course, by means of some classical variational technique, one can obtain the equivalent weak formulation of the strong form. And actually, this will be our starting point for the numerical approximation of such systems. So without loss of generality, let us also consider only bifurcation for the description, only bifurcation from the trivial solution, in the sense that now we are assuming that for ease of definition, the trivial solution is actually a solution for every parameter in the parameter space. And in this case, the bifurcation theory is the study of the existence of those values mu star such that non-trivial solutions are branching off from the trivial one. And we can actually also give a more precise mathematical definition to these points. And we say that the parameter value mu star is a bifurcation point for the strong form if there exists a sequence xn mu n with xn different from 0, so different from the trivial solution, such that the pair xn mu n is a solution to the strong form for every n, and the pair converges to 0 mu star. This is a definition back to the 90s due to Ambrosetti and Prodi. So, of course, we cannot deal analytically with such complex systems, and so we need to rely on finite-dimensional approximation, and in particular to the finite-dimensional space X of calligraphic N of dimension calligraphic N that is embedded in the solution space. And in particular, this is the algorithm that we developed to discover and to recover the bifurcation diagram, that is the implementation results of three well-known and assessed methodologies that are the Galerkin finite element method, the Newton method, and the continuation method. So let us explain it in more detail. So the first line is the choice of the initial guess. And this is a critical task because, in this way, we will seek and we will decide which branch has to be reconstructed. Then we encounter the continuation loop that in its simplest version consists in an out loop on the parameter space in which we are changing the initial guess to the nonlinear solver as soon as the solution turns out to be non-trivial, because in this case, this means that we have met the bifurcation point and we want to follow the post-bifurcating behavior in a proper manner. As regards the nonlinear solver, we choose the Newton method, which provides us a linear system with the variation as unknown, and we solve this linear system by means of the Galerkin finite element method. Of course, as we said also in the previous slides, we can study the stability properties of the solution that we have found by means of some suitable eigenproblem. So let me just give you a few details for the Galerkin finite element methodologies, just because this will share many common features with the next part. So we have our weak formulation that is projecting in the in the finite dimensional space, the finite element 1 actually, we can linearize by means of the Newton method around the previous iteration of the Newton methodologies, and we obtain this finite dimensional say abstract formulation in the second block. But we know that we can express every element in the finite dimensional space, in the finite element space, as a combination of its basis, and by substituting these inside the abstract formulation in the second block, we obtained the linear system that we can see in the last block in terms of the high fidelity Jacobian and residual, and this is a linear system, say where the unknowns, the variation is a vector in R of calligraphic n. So just few remarks on the computational costs. So here actually we have to deal with fine mesh discretization. In fact, in order to be sure to capture all the effect of the nonlinearities and so the bifurcation, the number of degrees of freedom has to be, say, typically quite large. But also we need to deal with nested loops in the sense that we have to solve this possibly huge linear system, so the one that you have seen with calligraphic n degrees of freedom, for every iteration of the Newton method, for every parameter in the parameter space, but also for every branch that we want to reconstruct. So this is actually a say many query and time demanding context. Regarding the continuation, we have some issues. In fact, we have to decide how to deal with multi-parameter settings. We have the choice of the continuation steps in the sense that if we consider a too small step, we may oversample the parameter space, and so we waste the computational time. While if we take a too big step, we may miss the bifurcation point. But finally, there are also, say, more theoretical issues, like the fact that the simple continuation method can fail when dealing, for example, with more advanced bifurcating phenomena, such as fold bifurcation, and in this case, are more advanced methodologies like the arc length methods are needed. Finally, the critical task of the choice of the guest. So we addressed it in several ways depending on the application. So the simplest one is, say, in the simplest one, we discretize analytic expression which share some common feature with the solution. Then we thought to taking advantage of the stability eigen problem, extracting the eigenvectors in order to have some information about the direction of the branching behavior. And finally, the deflation method, which is a powerful technique that allows you to deflate or precondition the system, in order to prevent its convergence to an already known solution. So somehow the deflation method is actually forcing you to discover new branches. So we can move now to the intrusive reduced order models part. So far, we have presented a really, time demanding and many query context. So it was natural to think about reduced order models, and in particular to reduce basis methodology based on proper orthogonal decomposition. That essentially is, again, another projection technique, but in this case onto a lower dimensional space x of n, spanned by some suitable basis function sigma m, where here the key assumption is that n has to be much lower than the degrees of freedom of the high fidelity problem calligraphic n. Here, I don't want to spend really so much time describing the reduced order methodology, but I will just give you some hints, and mainly also the differences between these and the bifurcating context. So the ideal pipeline is that we have our partial differential equation, possibly nonlinear. We have our solution space X, and the black line represents the solution manifold. Then we can project our weak formulation or our system into the high fidelity space, and we can sample the parameter space in order to actually evaluate some high fidelity solution corresponding to this parameter in order to obtain a representation of this solution manifold inside the finite element setting. And this is the so-called offline phase. Then this is the computational easiest and can be performed onto say into supercomputer. Then we want to rely on these pre-computed quantities in a non-intrusive way, so in a way that in which we are not rely on the calligraphic n quantities to say compute a new solution for x, say called xn, given a newly parameter mu. This is the reduced basis approximation, and we can perform this say inexpensively usually. But in this case, we are not in the common situation, but we are dealing with bifurcations. So the manifold is no longer smooth with respect to the parameter, and we have this intersection, and we have also to rethink the whole sampling procedure. So we say investigated two different approaches. The first is a global one, in which we consider all these snapshots that are actually the high fidelity solution for given parameter in the parameter value, and we consider all these all the branching behavior to construct our reduced basis by encoding and compressing all with a unique POD. Of course, this will have will cause higher errors and a larger number of basis function to be used. And but say we also investigated a branch-wise approach in which we only consider say snapshots coming from a single branch. In this case, we will have a low-dimensional space, but of course, in principle, we are not able to recover online say branches that were not sampled during the offline procedure. So just to remark also at the pod hierarchy level, as you can see, this is really the same slide, but in this case, we have the projection, since this is again a projection scheme, but this time onto the space X of n. We have our reduced step for the Newton method, and also here we can express the reduced basis solution as a weighted sum with respect to the basis function sigma m weighted by the reduced coefficients that this say it is they are the solution of the pod Galerkin approximation, so the previous step, and in particular in the algebraic form that you can see at the bottom of the slide, where Jn and Gn are the reduced Jacobian and residual. Let me also mention the fact that ideally in a standard situation you don't have this nonlinear problem, and so if you have the so-called affine dependency assumption, you can really inexpensively compute the solution for a newly given parameter. But in this case, we have to assemble all the quantities again, and so in this say nonlinear case, we have to say we have not the full decoupling between the offline and the online procedure, and so is not that say inexpensive such step. So just few remarks also at the reduced basis point. Of course, reduced output can be used for an efficient evaluation of the bifurcation diagrams. As regard the parametric sensitivity, well, the manifold is no longer smooth with respect to the parameter, and so we expect higher peaks in the reduced basis error. Regarding the potentiality, well, the reduced order model approach, say the bifurcating system really benefits from the reduced model approach when dealing with the multi-parametric settings, in the sense that we can encode in the basis the bifurcating behavior and then say translate to different configuration or physics configuration of the systems. As regard the sampling technique, of course, one can think to a more advanced way of sampling the points in the offline phase, like the greedy algorithm. But of course, for this one, have to develop an a posteriori error estimator, for example, based on the Brezzi-Rappareva theory. But this is a really complex task when dealing with bifurcation. And finally, as regard the efficiency, as we say, even if we have the fine decomposition assumption that hold for the parameter, we need to rely on a reduction technique like the empirical interpolation method to recover this efficiency. I don't want to enter in the detail of the empirical interpretation method, but somehow say, and in particular the reduction strategies, they are, say, a way to recover and to interpolate the nonlinearities in order to obtain an online phase which is calligraphic n independent, and so efficient again. And this will be, say, the starting point for our non-intrusive artificial neural network approach. So the goal, again, is to develop a reduced basis integrated neural network framework in order to deal with nonlinear PDEs undergoing bifurcation, and we want to avoid the applicability of empirical interpretation strategies. How we want to do this? Well, through the PodNN technique introduced in a paper done by Estaven and Dubbiali, where they try to learn this map that gives you the reduced coefficients for the reduced basis expansion of the solution. Why? Well, of course, because we want really this full decoupling between the online and the offline phase, and we want to recover in a non-intrusive and say real-time manner the bifurcation diagram. So up to now, we have seen how to pass from the high fidelity residual to reduced fidelity 1, and we have seen that we can express the reduced basis solution as a weighted sum of the reduced basis function, weighted by the reduced coefficients coming from the solution of the Newton system at the reduced level. But say with the PodNN approach, we want to build a surrogate solution, XNN, where we are still relying on the reduced basis sigma n, but in this case, we are changing the weights with this function pi that we want to learn from data. So before moving to the description of the PodNN approach, I would just want to give you a few remarks. So the first is that we can consider the nodal values of the reduced basis sigma n, and we can say group together all these nodal values for the reduced basis, and we obtain the transformation metric that essentially encodes the the change of variable from the finite element to the reduced basis coordinates, and so we can simply move to from the degrees of freedom of the finite element to the reduced basis 1 by pre-multiplying for the this transformation matrix. The second remark is that, as we know, the closest element of the reduced basis space x of n to the high fidelity solution x of calligraphic n is simply, say, in the finite element norm, is its projection onto the reduced basis space, and we can denote this solution as xv calligraphic n. That is again can be represented again as a weighted sum over the reduced basis, but in this case the reduced coefficients are given by the pre-multiplication of the transpose of the transformation matrix by the solution vector, high fidelity vector x of calligraphic n. So actually, we don't want to dive in the ocean of machine learning, and we don't want to go in depth with the networks and with the complexity of the structures. We in fact rely on the most basic, say, machine learning technique, that is a neural network, feed-forward neural network for supervised learning in a regression task. In this case, the goal is to approximate a function f from an input space to an output one, where all that we have is data, and in particular the pairs of the teaching inputs and the pattern input p of I, and the teaching outputs f of p of I. There are many possible ways in which we can embed this technique into the reduced order model settings. One of these is the PodNN approach, and in this case we use this feed-forward neural network to approximate the map pi that goes from the parameter space calligraphic P to the space of the reduced coefficients. So actually we want to build this map starting only from the data given by the parameter and the projected reduced coefficient of the high fidelity solution. So, of course, this Podernine technique is called like this because you have the neural network for the learning procedure, and the POD instead is say you are using the POD while constructing the snapshot X of calligraphic N, and of course the reduced basis encoded in the transformation matrix V. So I just want to give you a few hints about how a feed-forward neural networks works, and also why it is performing also quite good in our case. Well, a feed-forward neural network for a supervised learning approach is essentially an oriented and weighted graph with nodes, edges, and layers. And say actually you have to find a way to translate the information from the first layer, that is the parameter space, and the last layer that is the reduced coefficient space. And to do this, you need a propagation function that usually is the weighted sum of all the inputs coming from the nodes in the previous layers. But of course, you also need say nonlinearities in this model, and in fact, you can use the activation function defined in each nodes. In fact, you can think that if you only use a linear weighted sum at the end, you can only have a regression problem that learn linear maps. Instead, you are in this case obtaining, say, the output of this learning procedure is a map that is a combination and composition of linear and nonlinear maps. Of course, once that you arrive to the last layer, you have to quantify and to have a feedback on the performance of your network. And to do so, you have the error performance function that essentially is a function of the weights of the network, so the whole configuration of the network. And you hopefully want to find the best configuration for the weights that minimize this multidimensional problem that you have defined in the last layer. And you want to find this global minima in order to have the best accuracy possible. Let's also mention the fact that within this technique, you have to deal with a lot of hyperparameters. The hyperparameters are, say, for example, the number of nodes, the number of layers, the activation function, propagation one, the error performance, say, and also many others. And this is a bit the bottleneck, say, at least from my opinion, of the neural network methodologies, even if it is a bit mitigated in this case, because we always deal with really small networks, in the sense that we say our input and our outputs are really low dimensional due to their definition. So our recipe is essentially how we built our network for our test cases. The dataset, as we say, is constructed by the POD, and in particular, we split the dataset into a training and a validation set. We do this, say, we give to the first to the training the 75% of data, and we do this for cross-validation purposes in order to have, say, again, a feedback on how it is working the learning procedure, in the sense that we test the net while we are learning. We also test the network onto unseen data. Then we have the training procedure. We choose the mean squared error performance function that you can see at the bottom of the slide. That is essentially the difference in the finite element space. Say, of course, you have the L2 at the end between the output of the network and the projected snapshots. We implemented a mini batch procedure with epochs, in the sense that we don't want to change every time the configuration of the weights that we have found with the optimization procedure, but we want to scale them with a coefficient. It's the learning parameter that we can define also in a dynamical way through the epochs. In fact, the concept of epochs is like that say you pass the whole data set reshuffled every time and divided in a different way with the minute batch say procedure. As say the optimizer, we choose the Adam one is one of the most basic, and that is essentially a gradient descent method, and we implemented the early stop procedure with epochs to avoid overfitting, that, as you know, is one of the most common source of trouble when dealing with regression problem. So these two first points have to be done during the offline phase. So in this way, you really have the decoupling between the offline and the online phase, and what you say end up in during the online phase is just to evaluate a nonlinear function, so the network that you learn, and you can build your neural network solution. Let me also mention the fact that as activation function, we choose the hyperbolic tangent and the ReLU one, that are two examples of say the sigmoid function and also piecewise linear function. So with this motivation and with this conclusion, we can go to the results for the multiparameter for PodNN application to the multiparameter test case with the Navier-Stokes equation. So the first is the Coanda effect. The Coanda effect is the tendency of a fluid to stay attached to a nearby surface and to entrain fluids from the surrounding, developing a region of lower pressure. Actually, the Coanda effect is quite ubiquitous in our world. In fact, it can enter in say really complex also cardiac disease, like the mitral valve regurgitation. That is say this phenomena that happen when the blood jet, instead of going from one chamber to another of the heart, instead of going say just in a symmetric way and say just right, it attaches to the walls of the next chamber, and this of course can be a source of trouble for patients, but also for measurement. But I'm sure that you have also experienced the Coanda effect in your life when you try to wash a spoon, or you try to pour a bottle of wine and you just messed up, because even if you know that it can happen. And let me also mention the fact that say this kind of phenomena is used also from researcher from companies when they try to optimize the performance of their products, and for example for cars and the design of cars and iron carving. So
excuse me, can I say something?
Yes.
Hello, it's Martin. Just very briefly, this wine bottle stuff is not Coanda. That's surface tension and adhesion. Just for clarification, I was also looking up Coanda effects, and this kind of wine bottle effect, or this spoon effect, that's not Coanda.
Yeah, actually, yes. You say you have the fluids that attaches to the surface. Say, I found it like an example of
yeah, I have read that it can be easily mistaken for Coanda because it looks very, very similar. But it's actually surface tension and adhesion and cohesion effects of fluids.
Okay. Okay.
So I mean, that's just what I read, because you are just showing the same picture. So I was just thinking about it.
Okay.
Excuse me for the interact, but I was just wanted to say it. Yeah,
no problem. And okay. So actually, in fact, we are we want to deal with the first say problem, the cardiac disease, and the Navier-Stokes equation in the mitral valve regurgitation. So here we are modeling, say in a very naive way, the Hertz chamber, and in particular we have the first part of the domain is the inlet channel, and is representing the mitral valve, while the second part is the Hertz chambers. And in particular, if you consider the Navier-Stokes equation parameterized by the viscosity mu, it exists a critical threshold that in this case is mu star almost 0.96, where a wall-hacking behavior, say, occurs, as you can see from the videos. And in particular, you still have two coexisting states. That one is the straight flux, while the other is the wall-hacking. In this case, on the top, but you can see that is for a symmetric reason. Also, you can have on the bottom, and this is depicted in the bottom part of the slide with the bifurcation diagram, where with the green and the yellow branch, you can see that say we are depicting the both stable branches and wall-hacking behavior and asymmetric ones, while at the center we have the unstable middle branch that essentially is the straight flux in a symmetric configuration. So how we discovered the stability properties of this solution? Well, actually doing the stability again problem, and in fact, what we expect is that given a given the symmetric configuration, what we expect is that the asymmetric configuration, what we expect is that linked to a change in sign of the eigenvalues, we have a change in the stability properties of the solution, so the presence of a new solution. And in particular, in fact, for the symmetric one, you can see that we have a cross in the y-axis, over the y-axis of the rightmost eigenvalue, while for the stable asymmetric configuration, all the eigenvalues remains confined in the negative part of the complex plane. So, okay, this is the parametric setting for the Podenen approach, in this case with only one parameter for this quant effect. As you can see, we just have low dimensional space for the reduced basis dimension, both for the velocity and the pressure space. In fact, we built two different networks for without mixing the two reduced coefficients. And as you can see, the network is really a small one because we just have 2 layers and 7 neurons. Let me recall the fact that, as you can see from the left plot, we were able to obtain the wall-hacking behavior. In fact, for mu equal to 2, we have this line plot over a vertical line over the channel, and here you see a straight and symmetric flux, while if you go with mu equal to 0.55, you obtain this asymmetric configuration that in this case is the wall-hacking behavior to the bottom part of the domain. We compare the standard reduced basis and the neural network approximation. As you can see, both have good accuracy. In particular, the neural network has better mean error, while the reduced basis has better max error, while the reduced basis has better mean one. This is of course due to the fact that as we expected, the parametric sensitivity is no longer smooth in the bifurcation points, and so we can see that the peaks of the reduced basis error is actually at the bifurcation point. And of course, we have the same results for the pressure errors. Then we can move to the these kind of interesting applications, in the sense that we now consider multi-parametric setting in which we want to discover the bifurcating behavior with respect to a varying, parametrized geometry, in the sense that we vary the width of the inlet channel, and as you can see from the channel plots on the bottom, you have really different situation for the lowest viscosity that we consider, that is 0.5, and in such cases, when the width it's that large, you don't have the bifurcation, while for the lowest dimension of the inlet width, you have really an already developed bifurcation and wall-hacking behavior. Here we obtained for the Podenen approach a really good approximation property, almost 10 to the -2. And in particular, here I want also to remark that the comparison with reduced basis methodologies is even better. In fact, we obtained a really worse error for maximum error of 0.75 relative one, because say when you deal with bifurcating system, also at the reduced level, the Newton solver may not converge, and so you really cannot have, say, in a standard way the reduced coefficients, while of course the standard evaluation of the parametrized method we find through the Podenen approach really give us without any problems the coefficients. And of course, for the same reason, the reduced basis say strategies without empirical interpolation method allows us only to obtain a speed up of 1.5, while the Podenen one is 10 to the 6th. So let me just give you a few words on the second test case. This is really not that say studied as well as the Coanda one. This is a triangular cavity flow where we have say null velocity over the wall and an horizontal velocity over the lead. In particular, here we present the say the parameter space where we consider only the viscosity, and again we have a small reduced basis dimension, and also the network is again quite small. But the Podenen reduced basis error on the right is performing better than the reduced basis that is the one on the left. And this is of course because, say, if the learning procedure is doing in a good manner, actually you are learning from the best possible solution that you can find, that is actually the projection of the snapshot. So you are learning from the best solution, that is the projection one. And in this case, we are also moving towards the bifurcating regime, in the sense that, as I say, this is a really complex problems, and we considered say a 3-dimensional parameter space where we increase further the viscosity up to a Reynolds of 5000, and we also considered 2 geometrical parameters for the x and y position of the bottom vertex. Of course, here we need a much increased number of reduced basis dimension, and also a bit for, say, the same work for the network. But as you can see, we were able to obtain these really say complex bifurcating diagrams in which we are depicting for several height, and the colors are the position in the x-axis of these triangular cavities. And what is interesting is that, as you can see, also even fixing one direction, what you have is that it seems to exist a critical values for the width of the angle, such that if you cross, for example, in this case, if I remember correctly, is pi over 4 for the width of the upper right vertex. The vortex, instead of attaching to the upper part, just spread out all over the triangle. So now let me just give you a few words on the reduced basis manifold for the bifurcation diagram. And in particular, here, say we are trying to take advantage of the no-smoothness of these manifolds, in the sense that we want to build a detection tool to discover this bifurcating behavior. And in particular, since we know that the parametric sensitivity is no longer smooth with respect to the parameter, then we know that the curvature could be a good indicator to understand the position of the bifurcation. And say, in fact, for example, the black dots are actually the one obtained from the recovery of the full solution, so the plot on the right, while the blue one is the one that we discovered with this curvature say detection tool. And actually we obtain also a good approximation error between the two, that almost order of 10 to the minus 2. So these are just a few say conclusion and possible perspectives. In fact, we want to go say into the say introducing physics within the physical informed neural networks approach. We want to embed automatic machine learning in order to find in automatic procedure the best configuration for the hyperparameters. But we also are trying to develop say another algorithm in order to control the decay of the neural net PDEN error with respect to the number of bases used. So these are just few, say, a list of papers related to my PhD thesis, and I thank you for your attention.
Thank you. Thank you, Federico, for the talk. As usual, guys, you can unmute yourself if you want to ask questions to Federico. So let's see if someone unmutes. Yes.
Hi, Federico.
Hi, Davide.
I have a couple of questions. So, well, I'm not an expert of the method that you have used. So, I'm sorry if my questions are a bit trivial, but my first curiosity is about how you construct the reduced basis. So, how do you choose the snapshot? And the second one is related to something that you have mentioned at the beginning. So, for example, in nonlinear elasticity, there are sometimes some bifurcations that are invisible to a linear analysis. So the second variation is still positive. So if you study the Jacobian of the discretized model, you do see all positive eigenvalues. But on the other hand, you have a bifurcation, and it is very difficult to track it. Do you have any idea of how you can use your code to track this kind of bifurcations? Have you tried it or?
Okay, so regarding the first question, actually, so the point is that usually, since you want to reconstruct the bifurcating behavior, you need, at least for the reconstruction of the bifurcation, you need, say, you may need a uniform sample of your parameter space. You just can think to a one-dimensional parameter space. So the one with the compressed beam, you have the compression that is your parameter, and you just study the compression, how it evolves, and you find this point. And you construct the basis in a way that, say, you just run the algorithm with the continuation method during both the offline and the online procedure. So you just vary the refinement of the sample. So you can extract from snapshot the bifurcating behavior, and then you can refine during the online procedure a certain given point. So where you actually discover the bifurcation, but in this case you are computing with, say, more efficiently your solution. Of course, this change when you go with multi-parameter settings, because you have actually a bifurcating parameter and one that is taking care about the configuration of your system. So, for example, in the last case, we have the viscosity is our bifurcating parameter, and the other ones that are the configuration. In this case, one can think, say, of course, you can do it by again a uniform sample or any kind of sample in your parameter space in a 2- or 3-dimensional parameter space. But say a more say we also tried a combined method. It's a pod greedy approach, in the sense that you compress all the information coming from the bifurcating parameter, and then you sample different configuration of your system. In such way, you can have a more global information about your system. Instead, regarding the second question, say at the moment I tried this. Say, of course, the eigenvalue analysis is quite difficult. In fact, to obtain this kind of plot also for the Navier-Stokes system, it was really difficult, and we also investigated it in more complex problems with optimal controls, or also even with fluid structure interactor problems. And eigenvalue solver are, say, not that stable when you are dealing with such a big system. And so the problem is, I agree with you, is theoretical, but it's also computational at the computational level. So actually, the stability properties is something that I investigated only because I have this tool at hands. but the detection of the bifurcation through the eigenvalues, I did it just for the for simple examples, so for the von Karman equation, and in this case for the Navier-Stokes one. But when I dealt with, for example, hyperelastic models or in 2D and 3D, I only tried, I only see the output of my thing. In that case, was the maximum norm of the displacement, and in this case, I can track this bifurcation. But I also have to say that with elasticity problems, that say in such cases, you really this buckling is one of the most snap through bifurcation that you can see, and so this kind of reduced basis manifold bifurcation diagram could be a good option, because in such case you don't have, say, a forced system as a smoothed transition between the pre and the post bifurcation, while if you don't consider forces, you have really high gradients, and so this curvature detection tool could work really well.
Okay, thank you.
I don't know, maybe Martin wanted to talk?
Yeah,
okay.
I just want to briefly extend on what I said before, that there are actually many effects in physics which look very similar to Coanda. Mm-hmm. There's also the Bernoulli principle, and what I mentioned, that the fluids just these surface tensions, which look very similar to Coanda. So to simply say like everything which attaches itself to a convex surface is Coanda is very, very wrong. And it's can actually be really difficult if you look into the literature to really distinguish the different effects from each other, because they look similar. Yeah, I just want to say it. Yeah, that one should be careful with that.
Yeah, because I started to say some papers, and they were mentioning also this kind of application.
Exactly, and I read that this is a very common mistake.
Okay.
And I also did it myself in the beginning.
Mm-hmm. Okay, I see. Thank you.
Are there other questions for Federico? It seems not. So I think that we can thank Federico for its talk, and we see next Friday for the next AJS. Thank you all.
Okay. Thank you. Bye.